welcome to the last video in the three-phase circuits course on the topic of unbalanced three-phase system. So here in this part we are going to cover the symmetrical components. Let's start. What are the types of imbalance? We have voltage imbalance and current imbalance. So we covered in videos 11 and 12 current imbalance, unsymmetrical loads. So if we have a fault or have a problem in the load, so we covered that one in the previous videos. But here we are going to look for voltage imbalance. We are going to use what we call it symmetrical component theory. Symmetrical component theory. Thank you to Charles Fortescue. He introduced in 1918 in his paper Method of Symmetrical Coordinates Applied to the Solution of Polyphase Networks. And according to that one, he showed that any unbalanced three-phase system can be decomposed into three balanced sets: positive sequence, negative sequence, zero sequence, balanced sets. So we didn't understand what do you mean. We are going to detail that one in the next slides. So what are the symmetrical components? Let's detail it. If we have unbalanced voltage or current in magnitude, phase, or both, it can be represented by a set of three balanced phasor systems called symmetrical components, consisting of positive sequence, negative sequence, and zero sequence. Still, we didn't understand. Let us put it in a matrix form. If we have unbalanced three-phase voltages, for example, VA, VB, VC, so we can write that one as VA equals VA positive plus VA negative plus VA zero. So VA equals VA positive plus VA negative plus VA zero. So that one is VA. And the same for B and the same for C. In this case, VA, VB, VC, they are unbalanced, but they are consistent of balanced positive sequence, balanced negative sequence, and balanced zero sequence. We need to know how to calculate the positive sequence, the negative sequence, and zero sequence. Let us see. We can explain the metrics using the phasor diagram as shown here in the figure. We have three voltages, VA, VB, VC. They are not equal in magnitude and the angle between them is not 120 degrees in time. So we can decompose these vectors to positive sequence, rotating in this direction, and negative sequence opposite to the first one, and zero sequence. They have the same phase but the same magnitude. For each sequence, we have the same magnitude and shifted 120 degrees for the positive and negative, but for the zero sequence, we have the same angle. So for example, VA equals VA positive plus VA negative plus VA zero. So still we don't know how to calculate VA positive, VA negative, and VA zero. So still we don't know how to calculate VA positive, VA negative, VA zero. So we need to know how to calculate them. So let us define operator A equals 1 angle 120 degrees. So A square equals 1 angle 240. And A cube equals 1. So 1 plus A plus S square equals 0. Balanced system. So how to calculate unbalanced voltages or currents from positive, negative, and zero sequence? If I know the positive, negative, and zero sequence, so definitely VA equals V positive plus V negative plus V zero. I explained that one in the previous slides. For VB, it will be A square V positive plus AV negative plus V zero. For VC, will be AV positive plus A square V negative plus V zero. And you can do the same for the current. But the question now, how to find the positive, negative, and zero from unbalanced voltage? So we are going to take the inverse of this matrix. So in this case, V positive equals third VA plus AVB plus S square VC. And that one is V positive for phase A. If you like V positive for phase B, you are going to have the same amplitude and shift by 120 degrees. For V negative will be third VA plus A square VB plus AVC. For zero sequence, it will be third VA plus VB plus VC. So that one is a test for our system. If we are going to add VA plus VB plus VC and equals 0, this means our system is balanced. If we have a value, this means our system is unbalanced. We can do the same for the currents. We can find the positive, negative, and zero sequence. So the question now, how to solve the problem if we have information about VA, VB, VC, or if you have information about V positive, V negative, V zero. Let us see. So how to solve the problem? We have three cases. Case number one, if we have unbalanced source voltage, unbalanced load, we can solve the problem exactly like what we did in video number 11 or 12. Solve the problem per phase to find the phase currents. Then find the sequence currents. Or solve the problem using symmetrical components, find the sequence voltages, then find the sequence currents, and from that one we can find the phase current. But there is a question here. Do we need the sequence current? So we need to answer this question. Why do we need to know the sequence currents? If the system has phase currents unbalanced, so we still care about sequence currents. Positive sequence, negative sequence, and zero sequence. They tell us how the unbalance affect the system physically and operationally. Something like losses, heating, torque pulsation, neutral currents, protection behavior, and fault response. For example, if we have phase currents unbalanced, the system can give alert that we have a warning here that the currents are not balanced. But under the magnifier, the motor here experiencing a high fault. So positive sequence can tell us the normal balance operation. The negative sequence, that one is unbalanced, that stress the equipment. And for the zero sequence, we have neutral related effects and heat loss. So we need to know the positive sequence, the negative sequence, and zero sequence. In conclusion, sequence currents reveal the underlying cause of a problem. So we know what's happening inside. While phase currents only reflects its symptoms. So phase currents just tell us something wrong, but we don't know how severe that one. Case number 2. We have unbalanced source voltage feeding unbalanced load. We can solve the problem exactly like what we did in video number 11. Solve the problem per phase to find phase currents. Then find the sequence currents using symmetrical components. Case number 3. Unbalanced source voltage feeding unbalanced load with known sequence impedance. In this case, symmetrical components should be used. So we are going to solve the problem using symmetrical components, find the sequence voltages, find the sequence current, then we are going to find the phase currents. So this method is important for fault calculation and system analysis. Something like unbalanced motor, for example. Let's take an example. A three-phase system has phase RMS voltage of 220 volt 50 Hz, feeding an inductive load with impedance 10 plus J10 ohm per phase. Accidentally, the phase B voltage is reversed, so it becomes 220 angle 60 degrees instead of 220 angle minus 120 degrees. So we need to calculate the sequence and phase currents. So we are going to list the voltages. So VA equals 220 angle 0, VB equals 220 angle 60 degrees instead of minus 120, and VC equals 220 angle 120 degrees. So the phasor diagram, like what we see here, it's opposite to the normal phasor diagram where phase B is reversed. So the impedance is 10 plus J10, so it's balanced. So we are in case number 1, unbalanced supply voltage is feeding a balanced load. So definitely we can solve the problem like what we did in video number 11. We're going to calculate the phase currents, each voltage applied to the load impedance. So VA over Z, VB over Z, VC over Z. It's clear here that all the currents, they have the same amplitude, but they are not 120 degree phase shift. So phase A has minus 45 degrees, phase B is plus 15, and phase C is plus 75. So we are going to calculate these currents using the symmetrical components. We are going to calculate the sequence voltages, V positive, V negative, V0. So V positive equals 73.3 using these metrics, and V negative equals 146.7 angle minus 60 degrees volt, and V0 equals the same value, 146.7 angle 60 degrees volts. Clear that the system has severe imbalance because the negative sequence and the zero sequence, they have a high amplitude. Now we can calculate the sequence currents. I positive equals V positive over Z, 5.18 angle minus 45 degrees. I negative equals V negative over Z, 10.37 angle minus 105. And I0 equals V0 over Z, 10.37 angle 15 degrees. So we can calculate the phase currents from the sequence currents using these metrics. So IA equals 15.56 angle minus 45, and IB equals 15.56 angle 15, and IC equals 15.56 angle 75 degrees. And that one exactly matches what we calculated in the previous slide. But what I need from you now to look for these values, 15.56, 15.56, 15.56, and look for the sequence currents 5.18, 10.37, 10.37. This confirms why we need the sequence currents. So the system maybe didn't give you any alarm that we have unbalance because we have the same magnitude for the phase currents. But actually we have sequence currents. They are experiencing a high value in the negative and zero sequence. We can solve this problem using MATLAB platform. We're going to build M code here. So we are going to input the voltages, VA magnitude and angle, VB magnitude and angle, and VC magnitude and angle. Then we are going to put a vector here for VA, VB, VC, and then we are going to add the matrix, which is X matrix function of the A operator, which is 1 angle 120 degrees. Then we are going to find the sequence voltages, which is 1 over 3 X multiplied by F. Then we are going to find the positive sequence, VP equals sequence, that one in number 1, and negative sequence and zero sequence. After you have positive sequence, negative sequence, zero sequence, you are going to find a positive current, negative current, zero current, because we have the impedance is constant, Z equals 10 plus J10. So we are going to use another matrix, which is the inverse for this matrix. So we are going to use Y matrix here, 1, 1, 1, A square, A1, A square 1. So then we are going to find the phase currents from the sequence currents, and we can display them. So let's look for the results from the MATLAB code. We are going to input the voltages, as we have the voltage 220, angle 0, 60, and angle 120. And then we are going to find the positive voltage, which is 73.3 as we calculated, angle 0, V negative 146.67, angle minus 60 degrees, and the zero voltage is 146.67, angle 60 degrees. Then we are going to calculate the sequence currents. That one will be 5.18, angle minus 45, and 10.4, angle minus 105, and 10.4, angle 15. And that one is exactly matches what we calculated in the example. From that one, we can calculate the phase currents. So the phase currents will be 15.55 angle minus 45, 15.55 angle 15, and 15.55 angle 75. So the MATLAB code matches exactly what we did in the example using hand calculation. What will I watch in the next video? In the next video, we are going to cover the 3-phase circuits quiz. See you in the next video.